Welcome to a lesson with Dr. Powell. Let's take a look at how we can see a digraph and from its incidence matrix, determine how many connected pieces or components there are of the graph. For instance, we look at this, notice that there's three separate connected parts. Here's one, here's another one, here's another one. So there's no path or edge adjoining either of these vertices to these over here at all. This is like an island separate from this guy. Likewise, this is like an island separate from this guy. These are called connected components of the digraph. So we notice there's three of them. Well, let's create a vector space, all right, where the vertices right here, V1 through V7, are just, they're objects, but let's treat them like vectors, and let's suppose that they're linearly independent of each other. So you can take linear combinations of them, you can add them, and whatever else, and rescale them even, and we're going to say that they're linearly independent. The dimension of V is simply the number of vertices, because that's how we describe this as being a basis. Okay, so we know that the dimension of V is, the dimension of V is 7. But now let's take a quotient vector space of V with one of its subspaces. Now see the subspace. How did I get it? Well, if you look at the columns here of the incidence matrix, I just simply wrote out what they were. I mean, a 1 in this position right here means V2, and a -1 over here, this means -1 times V1. And so this column right here is represented by V2 minus V1. Similarly, this column is represented by V3 minus V2, and so forth. So basically what we're doing is we're going to take a quotient of V modded out by the range of this matrix under the column interpretation, or the column space, the span of the columns of this matrix. That's what we're looking at right here. So the range of this matrix as a function under the column interpretation. What is its dimension? Well, if we did Smith normal form on this, we look at the rank of this matrix by counting the number of ones, and that rank right there is the dimension of the range, so the dimension of this subspace of V. So let's take a look at that. So if we look at this, right here, what we have is this has dimension. Let's see, there's 4 ones, so dimension 4. This V right here has dimension 7. And vector spaces are really nice because when you're quotienting something with quotienting a vector space by something else, modding out by it, actually the dimension of the quotient space, what is the quotient space? It's just simply, you see this right here? This is like a whole subspace, and the subspace in the quotient turns into 0. And then if you take like different shifts of this subspace, those are going to be like the vectors in the quotient. So the vectors are actually like shifts of subspaces. Like if you add like a vector V plus the whole subspace, that whole set of stuff that's happening right there is actually a whole vector. And so we're describing, and so we have a whole vector space described by those. Now, the dimension of that vector space is actually just the subtraction of these guys. So 7 minus 4, this has dimension 3. Okay, well, all right. Well, oh, wait a minute. 3 looks like the number of connected components. So how does that work? Well, let's think about what we're doing. When we quotient or mod out by something, what we're doing is we're declaring that it's behaving like 0 in the quotient. So that's kind of like saying that V2 minus V1 is like 0. I'm going to use a bar to represent what happens to a vector after it runs through the quotient process. So in the quotient process, so you have a vector space and has lots of vectors in it. And what you do is you take a big chunk and then you take another big chunk. And you do this with all the vectors, so all the vectors are put into these chunks. And these chunks, basically these collections of vectors, become vectors in and of themselves in the quotient space. All right. So the vector that's going to correspond to the zero vector is going to be v2 minus v1 is actually going to fit inside of there. Now, one thing that we can do is notationally, let's see, which chunk has the vector v in it? Like, let's suppose I just take a vector lowercase v and say, which chunk is it in? Well, notationally, I can just put a bar over it and say, hey, v bar is the chunk that contains v. So if I use that notation, I know v2 minus v1 bar is going to be the same chunk as the zero vector bar. Okay, so these guys live in the same chunk. Now, the nice thing about this bar notation and this quotienting deal is actually these bars split pretty nicely, and they behave very well with respect to addition and subtraction and scalar multiplication. So here we could even think like this. We could think that's equal to z, and I'll forego the little vector symbol. Just remember the zero refers to the zero vector. So v2 bar minus v1 bar is equal to 0 bar. And if we add v1 to both sides, thinking of 0 bar as acting like an identity, because this is a vector space, adding it over, we end up getting that v2 bar is equal to v1 bar. So what we're doing is saying that if there's an edge, notice how I got v2 minus v1 from the graph. I got it because, look, there's an edge between v1 and v2. So if there's an edge, hey, that's like a connecting point, right? So if there's something that connects, then what we're going to say is we're going to say that the end of the edge, the vertex at the end of the edge, is going to be the same as the vertex at the beginning of the edge. So these two vertices are going to be treated like the same thing. So we can think, so in our quotient, we're going to say that v2 is going to be kind of like the same as v1. Well, likewise, v2 is going to be the same as v3 because we have this edge, meaning that all three of these vertices in this quotient will really be the same mega vertex, you could say, if you will. They'll live in the same chunk, and that big chunk is going to contain all three of them. So we have this big chunk that's going to represent that all three of these vectors are going to live in. So they're going to be treated as though they're the same vector. And so if you take this chunk that they all live in, maybe we'll call it, if you want, you can just give it a name like W1, representing the big chunk that all these guys live in. Then there's a big chunk that these guys live in, and actually this chunk will be different than this chunk, which will be different than this chunk as we go. Well, how do we know that? Well, for one thing, we know that we have at least three chunks, and all the chunks come from the vectors in V, and sure enough, I mean, we have these vectors spanning everything. So really, this kind of three chunks fills the whole thing. Do any of these chunks combine? Well, no, it can't, because the dimension has to be 3, as we just indicated. So we get 3 separate chunks, meaning that 3 separate vectors that must be linearly independent of each other as well, meaning that they form a basis for the quotient. These big chunks do. So really, the dimension of the quotient gives the number of connected pieces. Quotienting just kind of merges vertices together if there's an edge between them. So if there's an edge between them, this quotient space, this quotient vector space, what it really does is it just pushes vectors together that are connected right here, that are connected according to what we're quotienting out by. We're quotienting out by the information that links vertices together via edges. So quotient by that information, so make that information 0, combines these because it makes these guys be in the same chunk, and there we have it. We can tell that we have three separate components simply by looking at the incidence matrix. So even if we didn't have the graph and we had a gigantic incidence matrix, really big, and we wanted to work with it, we could run some processes on it quickly and determine what the rank of the matrix is. Now, from the rank and the number of vertices, we can tell how many connected components there are. We just simply take the number of vertices, which is the dimension of V, and we subtract off the rank of the incidence matrix, which is the dimension of the span of this information right here, that builds our connected pieces, and you get the number of connected components. So again, it's just number of vertices minus rank of incidence matrix equals the number of connected components. Thanks for watching.